The digital revolution has ushered in a paradigm shift that redefines the very essence of human legacy through the advent of artificial intelligence and digital twin technology. The concept of a digital twin, a meticulously engineered replica that mirrors an individual's personality, knowledge, and values, is no longer confined to science fiction. Instead, it represents an emergent field where advanced machine learning algorithms, deep neural networks, and complex data integration converge to create a persistent digital embodiment of one's identity. In this evolving landscape, every action, thought process, and even emotional nuance can find representation in a meticulously crafted digital model that captures the intricate interplay between cognitive processes and experiential learning. The replication process involves not merely superficial data retention, but a profound encapsulation of the continuous evolution of human intellect. Technical innovations in high-fidelity memory modeling and voice synthesis have paved the way for these digital replicas to sustain an authentic semblance of personal legacy. As custodians of their own digital twins, individuals are afforded the opportunity to project their existence beyond physical constraints, establishing a legacy that could potentially endure across generations. Concurrently, the precision algorithms and continuous self-improving systems inherent in digital twin technology emphasize the transformative implications of artificial intelligence on identity preservation. This script navigates through the sophisticated architecture underlying digital twin technology, exploring the nuances of personality encoding, data integrity, and algorithmic transparency. It also critically examines ethical dilemmas and societal implications that inevitably accompany the pursuit of a digital legacy, prompting a reflective consideration of what it means to be human in an era dominated by artificial intelligence. This transformative intersection of technology and human essence challenges conventional paradigms, calling for an analytical exploration of the underpinnings of self-representation in an era where data becomes a surrogate for the human experience perpetually. The genesis of digital twin technology can be traced to early efforts in systems simulation and finite element modeling, where physical prototypes were emulated in a computational environment for predictive analysis. Over decades, the convergence of increased computational power, more sophisticated machine learning methodologies, and the ubiquitous collection of digital data catalyzed its evolution into a tool of profound personal and industrial applications. Early research in biometrics and computational neuroscience laid the foundational principles for modeling human cognition and personality, which today serve as critical components in developing authentic digital replicas. Pioneering projects in high-dimensional data embedding contributed significantly to capturing the nuances of a user's behavioral patterns, establishing a framework that is as robust as it is adaptive. Simultaneously, advancements in speech recognition and natural language processing have endowed these systems with the capability to reproduce a voice that is both unique and reflective of an individual's emotional spectrum. Historical case studies demonstrate that exponential growth in algorithmic efficiency and data storage capacity has enabled researchers and technologists alike to venture into spaces where one's digital footprint is interwoven with legacy preservation. Methodologies that once only allowed rudimentary representations have now given way to intricate models that incorporate real-time learning, dynamic memory consolidation, and continuous self-optimization. The lineage of digital twin technology is not solely the domain of theoretical constructs, but has been rigorously applied in cyber-physical systems and personalized healthcare. This evolution signifies an important shift from static data archiving to dynamic, interactive models capable of simulating cognitive and affective states with high fidelity. As the field matured, interdisciplinary collaborations among computer scientists, neurologists, data ethicists, and cognitive psychologists further enriched the development of these models. The integration of domain-specific expertise has refined computational architectures that ensure scalability, accuracy, and security in the deployment of digital twins. Historians of technology now note that these advancements are emblematic of a broader trend toward human augmentation and digital immortality. Collectively, these developments reflect a trajectory where legacy is not merely preserved, but is actively reconstructed in digital form. Researchers continue to innovate, pushing the boundaries of what is possible in the accurate and ethical representation of the human persona. The historical evolution of digital twin technology illustrates a journey from basic simulation tools to sophisticated AI-driven replicas capable of introspective analysis. Early models served primarily industrial and engineering needs, yet they laid the groundwork for more personalized implementations. Over time, iterative breakthroughs in computational methods have drastically improved the resolution and adaptability of these models. This progression has seen digital twins expand beyond mechanical systems to embrace the intricacies of human behavior and decision-making processes. The combined efforts of multidisciplinary teams have been instrumental in integrating psychological theories with technical design, systematically bridging the gap between quantitative data and qualitative human experience. As innovation continues, the historical trajectory of these systems offers valuable insights into the future of digital identity and legacy, emphasizing the inherent interplay between technology, ethics, and the retention of human uniqueness, marking a new era now. At the core of digital twin architecture lies a multi-layered framework that integrates data acquisition modules, advanced processing units, and continuous feedback systems. The initial data collection phase is characterized by real-time input from diverse sources, including biometric sensors, interpersonal communication platforms, and contextual behavioral data aggregators. This heterogeneous data is then normalized through sophisticated pre-processing algorithms that employ statistical outlier detection and signal enhancement techniques to ensure integrity and accuracy. Subsequent to data normalization, advanced deep learning architectures come into play. Convolutional neural networks, recurrent models, and transformer-based algorithms collaborate to extract both temporal and spatial features crucial for encoding a user's persona. Attention mechanisms within these networks allow for the selective emphasis on high-fidelity signals, enabling the refinement of learned representations. The intermediate layers of the architecture are dedicated to memory modeling and dynamic knowledge consolidation, where episodic experiences are transformed into contextualized digital representations. At this juncture, variational autoencoders and generative adversarial networks are utilized for reconstructing nuanced behavioral patterns and simulating hypothetical scenarios. Furthermore, the integration of blockchain-based verification protocols ensures data provenance and integrity throughout the lifecycle of the digital twin. These cryptographically secure ledgers not only safeguard sensitive personal information, but also provide transparent audit trails for algorithmic decisions. One of the pivotal challenges in the system's design is managing computational complexity while maintaining a real-time feedback loop. This is addressed through parallel processing architectures and distributed computing models, which leverage cloud-based platforms and edge computing nodes. Specialized application programming interfaces, APIs, enable seamless interoperability between the digital twin and external analytical tools. Utility functions and modular plugins further extend the system's capabilities, allowing for dynamic updates as the underlying machine learning models evolve. The integration of high-dimensional data modeling coupled with reinforcement learning enables the digital twin to continuously adapt to new behavioral trends and environmental variables. Advanced error correction algorithms and iterative refinement cycles ensure that each update enhances both precision and personal relevance. As a result, the digital twin functions not as a static repository, but as an ever-evolving simulation that mirrors the complexities of human cognition. In summary, the technical infrastructure of digital twin systems is a symbiotic blend of data science, distributed computing, and advanced artificial intelligence methodologies, which collectively sustain a persistent, dynamic legacy in a rapidly transforming digital landscape. The architecture's modular design facilitates the integration of emergent subsystems and allows iterative enhancements without overhauling the entire framework. Through the adoption of scalable microservices and containerization, each component of the digital twin infrastructure can be independently updated and optimized. This adaptability is paramount in accommodating rapid advancements in AI research and evolving user requirements. Furthermore, Real-time data synchronization protocols reduce latency and improve the twins' responsiveness. The continual calibration of prediction models reinforces system robustness, serving as a testament to the architecture's resilience and future potential. Overall, the technical rigor embedded within the digital twin structure lays the groundwork for unprecedented digital legacy preservation. This additional capacity ensures that future complexities are seamlessly assimilated into the framework. The process of memory modeling within digital twin systems involves capturing episodic, semantic, and procedural memories, thereby allowing a comprehensive representation of an individual's life experiences and behavioral tendencies. These systems encase advanced relational databases paired with neural embedding spaces that convert raw experiential data into meaningful vectors. By mapping these vectors using manifold learning techniques, the digital twin is endowed with the capacity to recognize patterns, infer intentions, and simulate predictive behaviors. Moreover, the subtle nuances of personality traits are encoded through the incorporation of psychometric analysis algorithms, which quantify characteristics such as openness, conscientiousness, extroversion, agreeableness, and neuroticism. The confluence of these data points results in a dynamic and fluid representation of the digital persona that adapts over time. Simultaneously, ethical considerations arise with respect to data privacy, consent, and long-term custodianship of one's digital identity. Governance protocols are designed to enforce strict access controls and ensure that the transformation of personal data into a digital legacy adheres to evolving regulatory landscapes. Moreover, adaptive algorithms monitor for anomalous data behaviors, thereby reducing the risk of unauthorized manipulation of personality models. Contemporary research emphasizes that the digital twin must not only serve as an archival repository, but also as a living, interactive entity that evolves in alignment with its human counterpart's growth. This persistent mirroring of identity raises intricate ethical dilemmas, from potential misrepresentation to the unintended consequences of algorithmic bias. Research communities advocate for transparency in algorithmic decision-making and the development of standards that protect individual rights while enabling technical innovation. As the digital twin becomes an extension of the self, it invites a re-examination of moral responsibility, intellectual property, and the permanence of digital memorials in a hyper-connected world. In addressing these challenges, interdisciplinary efforts combine legal frameworks, ethical theory, and technical rigor to create a balanced, respectful, and secure digital legacy. Computational methodologies for memory modeling are anchored in probabilistic graphical models and Bayesian inference, which provide a statistical framework for quantifying uncertainty and behavioral variation. These models move beyond simple linear representations by incorporating nonlinear dynamics capable of capturing abrupt shifts in behavior. Unsupervised learning techniques, including k-means clustering and density estimation, identify latent traits in complex datasets. In parallel, reinforcement learning frameworks optimize response mechanisms through continuous reward feedback, thereby refining decision-making processes in real time. The integration of these methods fortifies the twin's ability to emulate subtle changes in personality and emotion over long periods. Moreover, encryption protocols and federated learning architectures secure the sensitive data underpinning these models and protect privacy during iterative updates. With a robust infrastructural design, the digital twin not only serves as a reliable archive of personal identity, but also functions as an interactive agent. This dynamic interplay between technical innovation and ethical governance ultimately determines the future trajectory of digital legacy, ensuring that the evolving representation remains both accurate and aligned with individual rights. This comprehensive framework supports continuous refinement and invites further research into harmonizing technological progress with ethical imperatives, ensuring inclusivity and enduring trust. Advanced research in digital twin technology has ignited vigorous debates regarding ethical dilemmas and the scope of future applications. As digital replicas acquire increased fidelity, issues of consent, data ownership, and long-term algorithmic bias have emerged as critical areas for scrutiny. Detailed quantitative studies reveal that even marginal deviations in subject data, often less than a 0.5% error margin, can propagate significant variations in the emergent personality states of digital twins. This phenomenon necessitates the development of rigorous statistical validation protocols alongside robust error correction frameworks. Moreover, ethical frameworks must evolve to address the challenges posed by the potential commodification of human identity. Researchers are increasingly employing multi-factor authentication, anonymization techniques, and differential privacy measures as fundamental safeguards in preserving individual rights. Further, the integration of explainable AI, XAI tools offers transparency into the decision-making algorithms that underpin the replication process. In highly controlled experimental trials, these tools have demonstrated a capacity to reduce misinterpretation of behavioral signals by up to 35%, thereby enhancing user trust. Beyond ethical concerns, future applications of digital twin technology promise to revolutionize sectors such as personalized medicine, autonomous systems, and cognitive computing. For instance, advanced replicas could serve as individualized healthcare avatars that predict medical conditions based on longitudinal data analysis. In the realm of autonomous systems, digital twins might facilitate real-time adaptive learning in robotic platforms, ensuring synchronized human-machine interaction. The multi-layered convergence of data analytics, deep learning, and real-time feedback underpins the potential for these systems to serve as digital custodians of human legacy. The interdisciplinary nexus involving AI ethics, regulatory compliance, and technical innovation is laying a strategic foundation that will likely define the next generation of digital identity management. As this field matures, a balanced integration of legal, technical, and ethical standards is crucial to harnessing digital twins as instruments of legacy preservation while mitigating the risks inherent to artificial replication of human consciousness. In addressing these advanced ethical challenges, researchers are also exploring legal frameworks that balance innovation with accountability. Comprehensive policymaking involves multi-stakeholder engagement, including policymakers, technologists, ethicists, and civil society representatives, to formulate guidelines that are both forward-looking and grounded in human rights standards. Quantitative risk assessments are being deployed to evaluate potential impacts, while scenario-based analyses simulate long-term societal outcomes of widespread digital twin adoption. This integrated approach supports the creation of standardized protocols and certification mechanisms that ensure digital twins are utilized in a manner that respects individual autonomy. Furthermore, advanced computational auditing techniques continuously monitor system performance and ethical compliance, detecting deviations that may signal emergent biases or operational anomalies. Ultimately, the confluence of legal, ethical, and technical strategies aims to foster a secure environment for digital legacy management, thereby ensuring that technological progress does not come at the cost of human dignity. These collaborative efforts are paving the way for a future where digital replicas are governed by transparent, accountable, and ethically sound practices, thereby reinforcing the integrity of digital legacies worldwide. This unified vision will shape emerging technologies and safeguard individual freedom decisively. In conclusion, digital twin technology represents a convergence of advanced computing, sophisticated data modeling, and innovative artificial intelligence that redefines the preservation of human legacy. The rigorous integration of deep learning architectures, detailed memory modeling, and robust error correction algorithms has enabled the creation of digital replicas with remarkable fidelity. As technical reviews have shown, even minute discrepancies in data can lead to significant variations, underscoring the importance of precision and ethical oversight. The interdisciplinary collaboration among engineers, computer scientists, neurologists, and data ethicists has established a framework that balances innovation with the imperative of human dignity. Moreover, the incorporation of blockchain verification and real-time processing ensures that these systems remain both secure and continuously adaptable. Future trajectories in personalized medicine, autonomous systems, and cognitive computing will undoubtedly benefit from these advancements, yet they also highlight the pressing need for comprehensive regulatory guidelines. The dynamic interplay between technological capability and ethical responsibility calls for ongoing research and dialogue. Ultimately, The digital twin serves not only as a repository of past experiences and learned behaviors, but as an evolving entity that mirrors the complex nature of its human counterpart. This enduring fusion of legacy and technology paves the way for a future where individual identity is both immortalized and subject to continual refinement in a rapidly progressing digital era. The convergence of theoretical insights with applied innovations assures that digital twins will persist as dynamic proxies, continually evolving to capture the multifaceted dimensions of human existence in every measurable aspect.